In this video, we'll be understanding how do we solve for a series problem circuit. So given a circuit, you'll be asked to find the total equivalent resistance in a given circuit. So using the concept of series parallel only, you should be able to crack the unknowns, that is the total equivalent resistance. So I am Professor Mohan B.S., working as assistant professor in Department of EEE STPIT. So let us understand how do we mark the polarities across any passive element, which are nothing but R, L and C. So in figure A, if the current is assumed moving from A to B, plus is marked towards A and negative is marked towards B, in the sense where the current hits or enters that side, or that at that side it is marked positive and the other side is marked negative. Similarly, for figure B, if you assume the current in this direction, that is from point B to point A, where the current enters or hits, that side is marked positive and the other side negative. Right. So these are important, not with respect to finding R equivalent, in order to find or know the voltage drop, and through that sometimes we need to find the resistance. So here in the given question, we have to find what is the total resistance across X and Y. So here let's understand a few topics related to node, junction and branch, and then proceed further. However, scan the QR code. It's already been discussed in one of the previous videos to know what is a node, a branch and a junction, much detailed. However, here I'll just explain what is a node. So node is just a mere endpoints of any element. So each element will have two ends. Resistance has two ends, A and B, for example. So that is called as a node. A mere connection or a mere connection of two elements forms a node. What is a branch? So in a branch, it will have two ends where the current remains same. So let's take an example here. So now I'll be writing different ways how we can say that these two resistors are parallel. I have represented four figures. In all the four figures, still we can say that two resistors are in parallel. So these two resistors are still in parallel, figure 3 or figure 4. So here you can see this is one node where two elements are connected, or point A, and at point B again the same two resistors are still connected. Thus we can say that they are parallel, and in parallel voltage remains same with polarity. In the sense here I'll have positive, and if I have negative, the voltage of course this resistance has positive polarity at the top, negative at the bottom. Similarly for this resistance also I'll have a plus and minus voltage drop. So these are different ways how we can represent, but still they are parallel. So this is one node which is common for these two resistors. The other end of this resistance is somewhere here, and the other end of this resistance is also at the same end here. Thus we can say that these two resistors are also parallel. So let me take another example to make you understand. So as I've drawn in figure 5, so now this is one end which is common for R1 and R2, and this is the other end which is common for R1 and R3, and this is one more node which is common for R2 and R3. Now what we can say, which all are in parallel? So here we have two branches. This is branch number 1 and this is branch number 2. So in branch number 1 we have only R1. In branch 2 we have two resistors, that is R2 and R3. And so here we can say if the current enters in this path, it remains same through R2 and R3. Thus we can say they are in series connection, just like how your metro trains or your double-decker buses, or how people standing in a queue, or how a person is sitting in a bench one beside the other. Right? Few examples to quote. So we can say that R2 and R3 are in series, thus they form one resistance. So I'll write here R2 plus R3, and to this branch, that is branch number 2, to this branch 1, that is R1, is actually parallel. So whatever is the voltage up across R1, it will be divided based upon its resistance value. So as we know by KVL, current remains same, the voltage divides. So more voltage will have more the value of resistance will have more voltage drop. So in this way, here we can say that R2 and R3 are in parallel series, and that is in parallel with R1. So we can simply write this as R2 plus R3, and this whole is two lines which indicates parallel with R1. So let's take up one more example. Now in this example, let me call this sixth example. I've changed my point B, which is connected at this node, right? So now R1 one end is here, R1 other end is here, and R3 is one end is connected to R1, and R3's other end is connected to junction B, or sorry, node B, and then to R2. R2's other end is here. So here, which all can we say which all are in series and which are in parallel? So we cannot say that these two are in parallel because they see opposite. I mean, they appear as if they are opposite to each other, right? So we can say here that R1 and R3 are in series. You can see water current flows through R1, it also flows through R3, right? So we can write here as R1 plus R3 together is in series. Two lines indicates they're parallel with R2. So let's take one more example. So here is the seventh circuit. So let me mark point A and point B. So this time I'll be marking point A here and marking point B here. And now what can we conclude? Which are in parallel with which and which all are in series? So we can say that R1 is actually in series with R2. R1 plus R2 are in series, and this in turn is actually parallel to R3. So you can see how the two measuring ends they have changed, then the R equivalent value will also equally change. So understanding this, let's go to the previous problem. So now here, this is one junction where you can see 1, 2, 3 elements are connected. This 12 ohm is connected here. I can also connect this 12 ohm here. I can also connect this 12 ohm in this pattern. I can connect 12 ohm here. I can also drag this along this line. I can drag along this line. I can drag it along this line. I can drag it along this line, and I cannot drag it beyond 60 ohms. So I cannot drag beyond 30 ohms, and I cannot drag beyond this 60 ohms. So 12 ohm I can actually rotate here. So in this way I can rotate, and I hope now it is clear that this is one junction or one node which is common for both 60 and 12, and the other end of 60 is here and the other end of 12 is here. And what is these? I mean, what are these actually? These are mere connecting wires. So I can still bring the 12 ohm in this pattern connect here. Thus, because of this connection, I can simply say that these two are in parallel. Now coming to the formula. The convention formula that you are all aware is R equivalent is equal to A into B by A plus B, which is nothing but 60 into 12 divided by 60 plus 12, okay, which will actually land up giving 10 ohms. But you can also use this formula, which is nothing but A inverse plus B inverse if they are parallel, and then whatever answer you get, its whole inverse, you'll again still get 10 ohms. The advantage of using this is actually n number of elements are in parallel. You can simply use one equation. If I have 3 elements in parallel, I can write A inverse plus B inverse plus C inverse, and then the whole inverse. I still get the same answer. So n number of elements are in parallel, I can use the same method to solve. So in this way we have seen the first step, that is 60 and 12 are in parallel, and the answer is 12 ohms, 10 ohms. Now, so thus 60 and 12 erases, we'll have land up with 10 ohms. Now what can you comment? How do we further simplify? So can I say 30 and 20 are in parallel? No, I cannot. Why? Because 30 and 20, one junction or one node is common. 30 ohms ends here and 20 ohms ends somewhere here. This is before 10. If you're saying that 20 and 10 are in series, you are right. So these two are in series. Thus we'll end up with 30 ohms. And now here, this, as we just explained, this node or junction is common for this 30 ohms and the upper 30 ohm. The upper 30 ohm end at this node here, and this 30 ohm, the bottom 30 ohm also has the same end. That's only because of that we can say they are in parallel. Now how do we do this? 30 inverse plus 30 inverse, the whole inverse, you get this as 15 ohm, or a shortcut. That is, I have 30 ohm which is in parallel, and the same 30 ohm appears twice. So we can simply write this as 15 ohm. For example, if I have 10 ohms in parallel, I repeat, if I have 3 numbers of 10 ohm in parallel, I would simply write this as 10 by 3 is nothing but 3.333 ohm. Just a simple shortcut to solve if more than 2 or more than 3 elements are in parallel and if the numbers are same. Now if I have 30 and 40 in parallel, let us say instead of this 30, if I have 40, so I cannot use this method, so I have to go with this particular method. So now 30 and 30 are in parallel, so we get 15. Now how do we solve this? Please analyze by pausing the video, and then you can resume back after your answer. So now we can say that 15 and 10 are in series. Water current enters 15, the entire current flows through 10. Or water, for example, if the water is entering through this pipe, okay, it enters through this tap, and the same water flows down, moves left, and also enters to this tap, right? Thus we can say that 15 and 10 are in series, and that the answer is 25 ohms. Now this 25 both are in parallel, because this is one common, these are the two common nodes for 25, and these are actually just mere connecting wires. So we can connect each 25 ohms in this syntax also, or redraw this to understand it much better. And here there are no connecting wires, whereas here these are actually the mere connecting wires. Thus we can say that 25 and 25 are in parallel, which is nothing but 12.5 ohms. So 25, the shortcut, 25, they are parallel, at both the times they are having same value. So 25 by 2, we will end up getting the value as 12.5 ohms. And now it's simple, 5, 12.5 and 15, all three are in series, thus the answer is 32.5 ohms. So let's check out one more example to find the total equivalent resistance across A and B. So please inspect the circuit clearly. So we have a wire or a switch which has been actually closed here, and this is actually called a jump. In the sense, there is no mere connection between the wires. So we have jump in the sense there is a wire which is over the another wire without any mere electrical connection. So there is no electrical connection between them. It's called as a jump. So then I want you to inspect this, try to analyze for series and parallel, and then we shall discuss further. Then once you have done with the analysis, please resume back to see the video. So now I've just taken the bottom triangle as 15, 22, and for the animation purpose I've just taken this. So what you can understand is 18 ohm is over 15. So I have a 15 ohm here, and over that I have 8 ohms. In a sense, it's free to move. So assume that you're pulling you're pulling the terminal A towards the right side. Okay, so in that case, this is the circuit, and now it is much easier to analyze. So it's easier to analyze now. This is one common junction, and what is this? This is just a mere wire. So I can also redraw this in this way. So for example, if this is point B, so then I have here 15 ohm, and this forms one junction. From here I have 35, this is point A. Again from point B I have 22, and this is 22. Where is it connecting? It's connecting to a junction for 15 and 35. So it goes here, and again from this junction, that is this junction, I have again 8 ohms coming out and meeting point A. Thus you can see this is one junction which is common for 35, 8, 15 and 22. And this is point A is one junction common for 35 and 8. Point B is common for 15 and 22. Thus we can say that 35 and 8 are in parallel, 15 and 22 are in parallel. So 35 and 8 we get 6.512, 15 and 22 we get 8.919, and thus now we can say that these two are in series, and the answer is 15.431 ohms. Let's take another problem to solve for equivalent across A and B for a given circuit. So I want you to pause the video, try to solve, and then resume back to verify. So now here, as you can see, we have a jump, right? So let us see how do we solve this. So I can move the other end of 4 ohms till here, that is I cannot cross 8 ohms, neither I can cross 6 ohms. So I hope you have observed now that this end is common for 4, 6 and 8 and 2, but for analysis purpose I'll take only the name of two resistors, that is 4 and 6. And the 4 and 6 also they're common at this node. I repeat, I'm talking about this 4 and this 6. So these two share a common boundaries or common nodes, thus we can say they are parallel, right? So I hope this image gives a clear indication that 4 and this 4, this 6 and this 4 are in parallel. Similarly, this 8 ohms, this line also I can move in this way. I hope now it is clear and evident that 8 and 2 are also parallel between point B and this node. So 4 inverse, so how do we solve this? 6 inverse plus 4 inverse, the whole inverse. Generally students they miss this inverse, so please keep a tab of the syntax. So 8 inverse plus 2 inverse, the whole inverse. Okay, so the answer is 2.4 and 1.6 respectively. So 2.4 for 4 and 6 and 1.6 for 8 and 2. Okay, so now how do we solve? So now it's clear that whatever enters through 2.4, in sense currents or water, it also enters to 4.6. Thus we can say 2.4 and 1.6, sorry, they are in series, right? So it becomes 4, and now it is clear between point A and point B, 4 and 4 are in parallel. 4 by 2, the answer is 2 ohms, or 4 inverse plus 4 inverse, the whole inverse, you still get same answer, that is 2 ohms. Thank you for watching the video. Please do subscribe to the channel to enhance your knowledge further.